All right, number 9. Find the area and perimeter in terms of r. So notice that we do have a semicircle here. We know that the area of a full circle would be pi r squared. However, because we only have half a circle, we must have half of that. So area equals half pi r squared. The perimeter of the circle, you tend to think of the perimeter more like the circumference of a circle. And we know the circumference of a circle is 2 pi r. And oftentimes people tend to think, oh, I have half a circle, so therefore my perimeter must be half of that as well, which is just going to become pi r. Well, just keep in mind that pi r is only taking into consideration the part that we have highlighted in red. We only have half that circle because we have, well, cut it in half, right? However, one thing you also need to remember is that there's this additional piece to create the perimeter on the bottom, and you can see that that's made up of 2 of our radii. So we need to make sure we add on 2 radii as well. That will give us the full perimeter of a semicircle. As we look at number 9b, find the area as a function of p. Unfortunately, our area is in terms of r. We don't want that. We need to change that r into a p. And how are we going to do that? How do we change the r into a p? There must be something we can do with this equation here. Notice in this equation we have variables p and r. So in other words, if we were to isolate r, we'd be able to get this equation in terms of p, and then from there be able to plug that in to our area equation. Okay, so let's go ahead and do that. Let's isolate r. In order to isolate r, what we'll have to do is notice that there's an r here and an r here. There's common terms there, so we can just factor that out. So if we factor r out, we'll get pi plus 2 times r, and then divide both sides by pi plus 2. And therefore r is p over pi plus 2. Okay. Now that we have the r value by itself, isolated, we can then plug this p over pi plus 2 into our r value there. So area is equal to half times pi times p over pi plus 2, like that. Okay. Oh, whoops, and it's r squared, sorry. So I need a squared. Okay. So you can leave your answer like that, or you can even simplify it just a little bit further. You can say that this is the same as pi p squared over 2 times pi plus 2 squared. You can do that too. Either form works. All right. Number 12. Find the domain of f of g of x if f of x is 1 over x plus 4 and g of x is 4 over x minus 2. So keep in mind that when you want to find the domain of your composite function, remember to consider the domain of inner function as well as composite function. Okay, so when you consider the domain of the inner function, which is g, and the inner function of g is right here, 4 over x minus 2. Its domain, we know that this is a rational function, and the only restriction we have is that x minus 2 on the denominator. We know it can't be 0, so therefore we know that x cannot equal 2. Okay, so that's something to remember, that the domain cannot have a value of 2. Now let's go ahead and find the f of g of x and then be able to find its domain. So we're putting g into f, so we're going to have 1 over, and then whatever x is, we're going to replace with g of x, so 4 over x minus 2 plus 4, and then we'll need to simplify this. So this will turn into 1 over 4 over x minus 2 plus 4 times x minus 2 over x minus 2, just getting common denominators there. Since we do have common denominators, we can simplify that. So we're going to end up getting 4 plus 4x minus 8 all over x minus 2, or I am running out of space, so I'm just going to turn this into 4x minus 4. 4x minus 4. So 1 over 4x minus 4, like that. Okay, and then simplifying further, we do have 1 divided by a fraction, so this is going to be the same as x minus 2 over 4x minus 4, like that. Okay. All right, so keep in mind that this is f of g of x. Since we're trying to find the domain, what is the domain of our composite function? Again, we are working with a rational function here, and we can see that the bottom is what's going to cause us the restriction that 4x minus 4 cannot equal to 0, which means basically that x cannot equal 1. Okay, so in terms of putting it all together, we know that the domain of g of x is basically going to be everything except 2. Okay, and then the domain of f of g of x is going to be everything except 1. So we want everything that overlaps these two domains. We can see the overlap occurs here, but then because x cannot equal 1, we have to stop it there. And then again, 2 cannot be part of our overlap, so we're going to have to stop it there. And then we have to overlap right here, and then just keeps on going from there. So therefore, our domain is going to go from negative infinity all the way to this value of 1. It cannot include 1. Union, we restart at 1, non-inclusive. It goes this way to 2, non-inclusive. Union, and then we restart at 2, non-inclusive, all the way to infinity. So this is going to represent the domain of our composite function for number 12. And I apologize for not having a whole lot of room here. In retrospect, I should have zoomed in and I could have written smaller. Sorry about that. But when you do number 13, I hope you have room for that one. All right, let's go on. All right, let's go to 2.1 here. I know that this is not exactly in our chapter 5, but it still utilizes the idea of composite functions, which is why we are doing this. Okay, so what we're going to work with is something called the difference quotient. You don't need to know too much about it at this point. It is used in calculus later, but all you need to know right now is the function, the quotient itself, the difference quotient itself, which is f of x plus h minus f of x, and we're going to take all that and divide it by h. Okay, so the only reason why we're doing this here is because we do see a composite function in there, and that composite function is basically that f of x plus h. We're going to put that x plus h into our function f. Okay, all right, so let's go ahead and begin. Now, because we have a number of different functions, f of x's in here, I'm going to explicitly label each of them. So my f of x plus h, if I put x plus h into my function, then that must mean wherever I see x, I have to put in x plus h. So f of x plus h is going to equal negative 2 times x plus h plus 1. Okay? And then I also have my normal f of x, which is just negative 2x plus 1. Okay, and the reason why I'm color coding this is because I'm going to now rewrite the difference quotient, which is f of x plus h, and then I'm going to do this in different colors, minus, and then we have the purple part, which is f of x, and we're going to take all that and divide it by h. Okay, and then from there, because I have color-coded everything, I now know that whatever is red, I'm just going to plug in, and whatever is purple, I'll plug in, and then it will all come out nicely. So I have negative 2 times x plus h plus 1, and then I have minus f of x. F of x in purple is, because it's an entire expression there, I'm going to have to put this in parentheses, negative 2x plus 1. And then all this is going to be divided by h. Let's simplify. So now we have negative 2x minus 2h plus 1. And then we have, and then I'm going to go ahead and distribute that negative to everything in there. So we'll have plus 2x minus 1. And we're going to take all that and then divide it by h. Okay, and then now we can start actually canceling things out. You'll notice that positive 2x and minus 2x, negative 2x, cancel each other out. So do negative 1 and 1, they cancel each other out. So all we're left with then is negative 2h divided by h, and h's cancel out, so all we're left with is negative 2. Okay, So we end up just getting negative 2 here. Just a fair warning though, I know right now we just got a numerical answer, but this is not always the case, so be careful when you're doing the difference quotient. You won't always just get a number. All right.